Okay.
All right.
Hey, good day, everyone in Cyberland, and welcome for the distinguished talk by the IEEE Solid-State Security Society and EDS South Brazil chapter. We are very honored and pleased to have a distinguished speaker with us today, Professor Paolo Crovetti. And let me advise you that in 2 weeks from now we'll have another distinguished talk on circuit design and RF and microfluidics. This talk today will be given by Professor Paolo Crovetti from Politecnico di Torino, is the Torino Polytechnic School, University, and he'll be talking about analog processing by digital circuits, a subject that he's been very active on for the last 10 years, and he has contributed a lot on the design, very innovative and creative ideas. A few words about our distinguished speakers. Professor Paolo Crovetti. He received the PhD degree in electronics and communications from Politecnico di Torino, in Italy, in 2003. He's an associate professor with the Department of Electronics and Telecommunications at Politecnico di Torino. He has contributed to our field of circuits with many important articles, and he currently has main research interests in the fields of analog, mixed signal, and power integrated circuits design. His recent activities will be, some of them will be talked today, are on non-conventional information processing techniques, allowing the fully digital implementations of analog functions on digital modules, and also on ultra-low power IC design for the IoT applications. He's a senior member of the IEEE and is serves as subject editor-in-chief of IET Electronic Letters in the area of circuits and systems, and he's also an associate editor of the IEEE Transactions on a Very Large Scale Integration, Transactional DLSI. With no further ado, I welcome everyone in Cyberland to our YouTube channel. You should have subscribe now, and I'll give the floor now to our distinguished speaker, Professor Paolo Crovetti. Thanks, Crovetti, for coming and being here with us this day.
Thank you, Sergio, for your introduction. Thank you a lot for giving me the opportunity to give this talk for the South Brazil Solid-State Circuit Electron Device Joint Chapter. As you anticipated in this talk, I will talk about analog processing by digital circuits, that is an alternative approach to address the challenges of related to the implementation of analog interfaces in IoT application by fully synthesizable integrated circuits. So let's start with the background of the IoT. We know that IoT is probably one of the big challenges of the years to come, as the vision that in which integrated circuits are embedded everywhere, so that require, process, and exchange useful information, so that to act as nodes of a globally interconnected network. The implementation of this paradigm implies very strong, very stringent requirements to IC designs, since we are talking about nodes that are in the cubic centimeter down to the cubic millimeter scale, so that to be placed everywhere, they need to be energy autonomous. For sure, they cannot be powered by the grid. It means they should be powered by tiny batteries or energy vessels. That means practical applications that the average power consumption should be in the microwatt range, or even in the nanowatt range for very small nodes. This tight power constraint means, together with the fact that the nodes are expected to be always connected, means that their operation should be highly reconfigurable. It should be possibly duty cycled or event driven, and possibly some strategies should be implemented so that to perform actions and to consume power only when it is strictly required, duty cycled operation or energy quality scaling approaches. Last but not least, a very important requirement for IoT nodes is that the cost of the node should be very, very low, it's expected that the number of interconnected nodes should be in the tens of billions range in the years to come. The cost of the node should be very, very small. It means that they should be implemented using mainstream CMOS technologies, and it means also very important that the design costs should be minimized. When we consider these requirements and we consider the how these requirements can be met by analog integrated circuit design, we can see that there are significant challenges to be addressed, since unlike digital ICs, analog ICs do not take advantage of geometrical scaling. There is almost no area reduction if we move from if we move to more advanced, more scaled nodes, and this means that the area of analog becomes more and more relevant in more advanced technologies. Moreover, we have that nanoscale devices typically show worse performance for what concerns analog applications, low intrinsic gain, maybe higher leakage, and the same power supply voltage scaling that is required when geometrical scaling is adopted. By reducing the swing of analog signals leads to a degradation of the signal-to-noise ratio. Moreover, we have that analog circuits do not take advantage by, in terms of power, by the reduction of the power supply voltage. And this is not just related to the theory. Of course, there are limitations, theoretical limitations to the minimum power consumptions on analog blocks for a given signal-to-noise ratio, but the most critical limit is related to the fact that analog circuits need to be biased at a constant operating point. That means that voltage and current references are needed for proper biasing, and these circuits draw a constant current that gives rise to a floor to the power consumption of the node. Moreover, the analog circuits show a limited reconfigurability, or if they are designed to be configurable, the design is becomes more complex, unlike digital circuits. And very important, the analog design flow, which is in great part manual, requires a significant effort and manpower. Moreover, more effort could be related to post-fabrication calibration to improve matching, for instance. So it means that the design and fabrication costs for analog ICs are going to be much more relevant compared to the automatic design flow that can be adopted for digital circuits. All of these constraints have used these limitations of analog circuits in recent years. There is a constant trend towards solutions in which analog processing can be replaced by digital or mostly digital solutions. For instance, I can mention in 2004 the introduction of the all-digital phase-locked loop, or in 2010 the introduction of the digital low dropout regulator, which indeed are nowadays quite common building blocks in IoT applications. And in view of this trend, one can ask, somebody has also asked these papers in conferences, if given that analog circuits are more and more the bottleneck in terms of cost and performance, we wonder if we really still need analog circuits in the Internet of Things era. And the common answer to this question is that yes, we will always need analog circuits, at least in interfaces toward a physical world that is intrinsically analog in itself. Well, I will start this talk by challenging this statement that we are living in an intrinsically analog physical world. And based on that, I will propose several new ideas to address the problem of analog interfaces in IoT applications by fully digital solutions. So let's start this some considerations of an intrinsically analog physical world. Are we sure that we are in an intrinsically analog physical world? We know that the matter is discrete, is made of atoms. This has been suggested more than 2,000 years ago. And nowadays it's something that is absolutely an evidence. We can see atoms. In this slide, you can see silicon atoms, for instance, at the scanning tunneling microscopy. Also fundamental physical quantities like the charge of electron, the electromagnetic energy are not continuous in themselves. We can think, for instance, to the charge that is stored in a capacitor. We commonly describe it as an analog signal, a continuous signal, but in practice, if we consider that electrical charges are discrete, it could be probably more accurate to consider it as a discrete quantity. Okay. Now, not only in nature, in let's say the physical world, the information is encoded in there is an intrinsic discrete structure, but also in the very same way that which animals and also humans encode and process information in their nervous system. The approach is substantially digital. From the work of Hodgkin and Huxley, 1948, we can observe that the activation of neurons is actually made by a sequence of pulses. So it can be considered as a digital signal. So we may conclude that a discrete, that is a digital underlying structure, is the basis of our analog feeling, of our analog experience. But probably what is more relevant for our discussion on analog interface is that information in itself is discrete. If we have a noisy channel, band-limited noisy channel, as Claude Shannon pointed out at the beginning of the past century, the maximum amount of information that we can transmit from the transmitter to the receiver, no matter if we use analog or digital signals to encode it, is finite quantity. Since analog signals are assumed, are supposed to transmit an infinite information, it means that if we use analog encoding, actually we are necessarily losing some information. So by properly taking into account these limitation, this intrinsic limitation of information, actually, and by designing information and communication processing systems taking into account of that, these led to what we call the digital revolution that has so deeply changed our way, our lives. But the consideration that I want to put to your attention in this talk is that the results of Shannon on the fact that the information is discrete do not apply just to computers and to communications, but they also apply to sensors, to actuators, and to operational amplifier, to amplifiers, to whatever we normally regard as analog systems. Systems which are used as interfaces in the Internet of Things. A digital revolution for this interface has yet to come, and this is the approach that I would like to propose in this talk and to explain. Actually, let me be more precise about what I am going to talk about. I'm talking about processing arbitrary electrical signals, which can be voltages or currents, to get arbitrary band limited and finite in amplitude, of course, output signals at a predetermined level of accuracy by using a circuit that is a truly digital circuit. That means a circuit in which information is internally encoded as a binary signal, can be synchronous or asynchronous, can be combinational or sequential, can include registers, memories, finite state machines, without using digital gates as analog circuits. That is, for instance, we should not use a CMOS inverter as an amplifier. Okay, possibly we can allow to include in this system minimal and non-critical passive network that can be regarded part of the sensor or part of the actuator, if you want. Okay. In this, this is the approach that I have tried to follow in the last 5 years of research, and I would like to show the results concerning how, by using this approach, this fully digital implementation can be adopted from common world analog building blocks like an analog differential circuit or a voltage reference circuit. Then I will also discuss about a new bit stream digital to analog conversion technique, which can be very, very useful in the practical application of this paradigm. So let's start with the digital-based analog differential circuit. Let's consider, for this purpose, an operational transconductance amplifier. It's a key building block in analog electronics, as we all know, and is mostly used as an error amplifier in negative feedback circuits. We all know that basically the circuit is expected to provide an output current which is proportional to the difference between the voltages at the plus and minus terminal, and it is insensitive to the common mode component. For instance, it can be implemented at transistor level by this simple circuit. If we want to try to translate this circuit into digital, the first step is to start rather from the circuit analysis, the small signal analysis, from a behavioral description of this circuit. That is something probably more close to the physical world. By following this approach, we can observe that how does it work? How does this circuit work? Well, we can consider that the common mode input voltage, the signal component of the common mode input voltage, is rejected by the input stage, since basically the common source node of the input devices track the common mode input, and this input is subtracted from the external input in the gate source voltages of the input devices, whose drain current is therefore affected just by the differential input voltage. Okay, and the slope of the differential current versus differential voltage characteristic is related, of course, to the device. And in an ideal OTA circuit, we expect that this slope is as high as possible. So if we try to simplify this behavior, we can say that in this circuit is intended to provide an output current that is plus the bias current if the input differential voltage is larger than 0, and is minus the bias current of the input stage if the input differential voltage is less than 0. In other words, if we consider the capacitive load that very often is applied as a load in this circuit, we can say that the output needs to be increased when the differential input voltage is greater than 0, and it should be decreased when the differential voltage is less than 0. In other words, we can encode the behavior of analog behavior of this block by this simple code. Let's analyze this code, and let's discuss how does it imply. First of all, it implies that we have to check if the differential voltage is larger than 0 or it is less than 0, and then we have to consequently drive the output so that to increase it or so that to decrease it. Can we translate this into a digital function? Let's try to answer this question by considering by applying the input signals of our differential circuit to a couple of digital buffers that are expected to have an ideal threshold behavior. The output is 0 if the input is below the threshold, is 1, logical 1, if it is above the threshold. Okay, now the question is, can we decide if the differential input voltage is larger than 0 or less than 0 looking just at the output, at the digital output of these two buffers? Well, the answer is if we check all the possible values that can take these outputs, we can observe that if the two outputs take two different logical values, for instance, out plus is 0, out plus is 1, out minus is 0, we can, of course, say that the differential input voltage is greater than 0. Similarly, if out plus is 0 and out minus is 1, it follows necessarily that the differential input voltage is less than 0. So if just these two output combinations would be allowed, we could implement the digital analogous of operational transconductance amplifier by driving an output stage so that to increase the output voltage when out plus is 1 and out minus is 0, and to decrease the output differential voltage in the opposite case. That is, implementing this digital behavior. Actually, there is a problem. The problem is that the output of these two digital buffers can be also 0, 0 and 1, 1. Let's discuss what does it mean when the outputs are 1, 1 or 0, 0. Actually, the outputs are 0, 1 and 1, 0 if the common mode input voltage is close enough to the trip point of the inverters. And in this case, the output, the circuit can work as a operational transconductance amplifier. When the common mode voltage is either is in any case too distant from the trip point, we have that the dominant common mode input component basically makes the circuit blind with respect to the differential output component. By the way, in these two situations, we can retrieve from the logical value of the output some information, some valuable information about the common mode output, the common mode input. If the outputs are 1, 1, it means that the common mode input is is larger than the 3 point, while if the outputs are 0, 0, it means that the common mode input is less than 3 point. And this information can be exploited so that to generate a compensation signal to be added, and in this case I have shown the simplest way this can be implemented, and to be added to the external inputs, so that to compensate the input common mode voltage and make the circuit operate in this condition. Okay, this behavior can be found to be analogous to the behavior of the differential pair in the traditional operational transconductance amplifier implementation, where the common mode is subtracted from the external input to give the gate source voltage of the input devices. Okay? Now, if we put together the output stage that is driven when the information brought by out plus and out minus about the external input is valid, and put together the common mode compensation circuit, we can have a digital-based analog differential circuit. Actually, the correct operation of this circuit can be simulated. Actually, what happens is that the out plus and out minus signals oscillate between the 0, 0 and 1, 1 state, but in the transition, when they transition the trip point of the inverters, there is a short time interval. There is a kind of amplitude to time conversion in which the logic level of the two outputs is different, and in which the output stage is driven properly, as it can be shown here. Just in these time intervals, the output stage is driven. If we connect this circuit in a negative feedback configuration, and we apply appropriate input signals, we can observe that actually this circuit works and behaves as an operational transconductance amplifier. Okay, this circuit has been studied. I will not I have not much time to enter into details, but it can be observed that the analog performance of this circuit can be translated, can be related to the digital performance of the digital gates employed in it. In particular, the unit gain frequency is related to the delay of the common mode compensation loop, and the gain is related to the ratio between the rising times of the common mode compensation loop and the output stage. We can also say that as for an ideal OTA, the ideal behavior corresponds to the assumption that the analog, the amplification tends to infinity. For this kind of amplifier, the ideal behavior corresponds to the condition in which the delay and the rise-fall times go to 0. This circuit has been actually implemented. At the very beginning, I'm talking about 7 years ago, 2013, I have implemented it using off-the-shelf components. And what is quite surprising is that it works as expected properly, even taking off-the-shelf digital components. Of course, the performance is not excellent, but this proves, this is a proof of concept that proves that these analog function can be implemented in digital terms. Now let's go ahead and let's consider the implementation of this circuit, the real integrated circuit implementation of this concept. More recently, this has been done by PhD student of mine. It's been implemented in the same concept in 180 nanometer CMOS, and the resulting circuit has been shown to operate as an operational transconductance amplifier at working down to 300 millivolt VDD and driving a capacitive load up to 80 picofarad with less than 5% distortion and consuming just 2 nanowatt power, yielding figure of merits that are absolutely competitive if compared to operational transconductance amplifiers working at such a low power supply voltage below 500 millivolts. And another very interesting thing is that porting this concept to an advanced, more advanced technology node from 180 nanometers to 40 nanometers, what happens is that all the figures of merit improve. It's very consistent with the digital operation of this circuit. Recently, we have also taped out this idea, and we had preliminary results, measured results, which confirm the simulation results. And we have also extended the concept, basically by replacing the input summing network, which was made by resistors that are not conveniently integrated in integrated circuit technologies. So with Muller-C gates, we obtained an amplifier that is based on the same concept, whose operation can be described by a state transition diagram as a finite state machine. And we have already measured the performance of this prototype that reports operation down to 300 millivolt is suitable to drive 150 picofarad with less than 2% THD, shows the lowest power consumption among amplifiers working at such low VDD, the lowest silicon area, and achieves again the best figure of merit below 500 millivolt VDD. The DC gain is still 30 dB, that is comparable with amplifiers working at the same supply, but probably from an application point of view is still too low. But we have also demonstrated that this circuit works properly if powered by a tiny solar cell, 7 square millimeter solar cell, under in a dark room without it has been tested the evening, the room was dark. So this suggests that based on this concept, we were able to address the requirements, we're truly able to address the requirements of IoT applications. Okay. Now let's go ahead with another concept. Let's talk about voltage references. I know that in Brazil there are many researchers working on this interesting topic. Let's try to discuss if also for what concerns voltage and current references, is it, which are, of course, as we know, cornerstones of analog electronics, if we can translate also these circuits into digital, it can be applied digital concepts to these circuits. Well, for this purpose, let me introduce one new concept, that is the concept of the virtual voltage reference. Let's assume to have a system in which we have a digital to analog converter. I will show immediately at the end of my talk that this digital to analog converter can be implemented as a fully digital circuit, so following the paradigm I have introduced at the beginning. Let's suppose to have this digital to analog converter that is working with a reference voltage that is not accurate. For instance, that is obtained by a voltage divider of an inaccurate supply voltage, and provides an output, of course, that is n divided to power n times this inaccurate voltage. With reference to this circuit, we can define as a virtual voltage reference a binary number R that, if converted into analog by this digital to analog converter referenced to the inaccurate, to the pseudo reference, provides an output voltage which is independent of process supply voltage and temperature. In other words, it's a constant reference voltage. Of course, the virtual voltage reference is a quantity that needs to be evaluated in real time, that depends on process voltage and temperature. We can conclude that if we know such a virtual voltage reference, we can convert it into analog using the digital to analog converter, and we can obtain any reference or any scaled version of the reference that we want. So it's a fully replacement of a truly analog voltage reference. Now the point is how can we calculate this binary number R? And the answer is by translating into digital the operation of a bandgap voltage reference, like the Q6 circuit that I have shown you from the beginning. I will illustrate this focusing on how to compensate, how to get a temperature independent output voltage. But I would like to stress that the same approach can be refined so that to obtain an output voltage which is also independent of the supply voltage and of process. For the sake of illustration, I will discuss just the temperature compensation. We know that in bandgap circuit, in particular in this Q6 bandgap circuit, temperature, a first order temperature independent reference voltage is taken by summing the forward voltage of a PN junction that is known to have a negative thermal drift, complementary to the absolute temperature, plus proportional to absolute temperature voltage, which is obtained taking the difference between the forward diode voltages of two junctions in which are operated under different current density. If we sum together these two terms with opposite thermal drift, and we choose this coefficient properly, we can get a reference voltage that indeed is about 1.12 volts, is close to the bandgap voltage of the silicon, which is first order temperature independent. Now let's try to translate into digital this approach so that to evaluate a virtual voltage reference. Now let's suppose to have an analog, digital hardware platform that includes a digital to analog converter, an analog to digital converter, and a digital processor. Both the digital to analog converter and the analog to digital converter are referenced to the inaccurate pseudo reference V0, that in this case is sampled, is capacitor. And let's suppose that a diode, which can be regarded as a physical standard, as a sensor, if you like, is connected so that to be biased by the digital to analog converter, and so that its forward voltage can be converted into digital by the analog to digital converter. If we apply a procedure that consists, if we convert first a certain number M1 into analog with the digital to analog converter, and then we convert another number M2, and then we acquire the corresponding output of the analog to digital converter, we can have the digital values corresponding to VD, the junction voltage, to the diode voltage at under the first bias M1, and to the diode voltage under the second bias M2, at different current densities. Okay, if we assume we can sum together, obviously from the diode voltage we can also derive the difference between two diode voltages, and if we suppose to sum together this voltage VD at the first bias and delta VD between the first and the second bias, we can get a reference voltage exactly as for the traditional bandgap circuit, which is temperature independent. But actually we do not have VD1 and delta VD as analog voltages now. We have converted them into digital. What happens if we replace VD1 and delta VD prime with, we express in terms of their output of the ADC, referenced to the pseudo reference V0? Well, actually, we can write this expression that can be further put in this form, that gives that the accurate temperature independent reference voltage is given by the pseudo reference V0 times a number. All this is a number that can be calculated, and it is nothing but our virtual voltage reference. So by repeating this procedure, we can evaluate this virtual voltage reference, and we can obtain a virtual voltage reference. Once we have obtained the virtual voltage reference, as we know, we can generate an output voltage proportional to this temperature independent reference, and if we acquire any input with the ADC reference to the pseudo reference, by knowing the virtual voltage reference R, we can translate the reading of the ADC reference to V0 to a reading reference to the accurate temperature independent voltage reference. Okay? Well, in other words, in this way we have translated the behavior of the QC band gap into a software procedure, into an algorithm. Okay, actually, this algorithm is a little more complex because it involves also the compensation of the supply variations, which I have not discussed before. This has been implemented in simulations, and can be observed that depending on the resolution of the analog to digital converter and the digital to analog converter, we can actually get, by reconverting the virtual reference, we can get a temperature independent voltage reference, which shows first order temperature compensation, and as a thermal drift of 22 parts per millions per degree in the -40, 140 Celsius degrees range. And also considering that we do not have two diodes or two transistors, but we have just a single device, this approach is very robust against the process variation. It's practically insensitive to process variation. Okay, this has been implemented. I have implemented it in a microcontroller-based proof of concept prototype that I have tested over temperature and over power supply voltage variations. In this plot, it can be observed the pseudo reference that is actually the supply voltage of this board is not obtained through a analog reference circuit, shows a relevant thermal drift. The virtual voltage reference that is computed by the algorithm inside the microcontroller for each temperature shows a different thermal drift by complementary thermal drift. By reconverting the virtual voltage reference with respect to the pseudo reference, we get the temperature independent reference voltage. Okay, well, actually I have not verified on silicon this approach, but I have realized that the very similar of the same concept has been adopted by colleagues at TU Delft that have implemented it on silicon. And actually, it's quite surprising that the measured thermal drift of the silicon prototype is in very good agreement to what has been obtained by the microcontroller-based prototype. So, what are the advantages of this approach? Very low area overhead, especially if in a system in which you have already an analog to digital and a digital to analog converter. But even if it is not available, this can be the area overhead can be very, very small. And since the compensation is based on digital algorithms, a very high accuracy can be targeted if more complex algorithms are employed. I have not shown for reasons of time, but this can be done. And this is the voltage reference can be calculated just when needed, so it is intrinsically duty cycled operation. So the average power consumption of this system can be very, very low. Now let's go ahead. We have said that digital to analog conversion, as we have seen also for the virtual voltage reference, is a key concept in the implementation of digital-based analog functions. Actually, this is not a completely new idea. We have digital PWM and single bit sigma delta converters that are based on this concept, that is to obtain an analog voltage by properly filtering a digital stream, so that to get an analog output which is basically proportional to the number of digital ones in a given time, in a time interval corresponding to the impulse response of the filter over the duration of the impulse response. Okay. What we need in digital-based analog interfaces anyway is not just a bitstream digital to analog conversion technique, but we need something that can be implemented with very simple hardware, so that to target low power, small area, and automated design. And we also want that the constraints, the requirements on the filters that need to be put are non-stringent. Otherwise, you know, if we need very low-cost technology, this is not suitable to low-cost technology. This, the first requirement makes sigma delta converters not so attractive for this target. The second requirement makes digital PWM-based converters not so well suited to this application, since in order to retrieve the analog output, there are very stringent constraints on the output field. Now, in view of these limitations of these two mainstream digital to analog conversion techniques, we have proposed a new digital to analog conversion techniques that is named dyadic digital pulse modulation. We can introduce it as a way to overcome to release the stringent filtering requirements of digital pulse with modulation. Okay, let's suppose we consider a 16-bit stream. We want to get an output that is 1/2 VDD. In order to perform bitstream based DR conversion, perform digital pulse width modulation based DR conversion, we need to have 8 slots at 1 and 8 slots at 0. If we take the spectrum of this signal, of course this is repeated periodically, we can see that most, of course, what we want is the DC, that is the analog value, converted analog value. The most of the energy of unwanted spurious components is at the fundamental frequency. That means very close to the bandwidth and very hard to be filtered. If we want to keep the DC and we want to reject this frequency that is very close to the DC, this is very challenging. It requires a very, very selective filter. Okay? But this is not the only possible way to perform digital stream-based digital to analog conversion. Instead of using, we have any other pattern including the same number of ones, for instance, the one which is reported here, in which we have evenly spaced 1 pulses, we may have that the spectral content is pushed all to a much higher frequency. That means it is much more easy to be suppressed. If we apply the same reasoning to the output corresponding to 1/4 of VDD, 25% duty cycle, we have the very same situation. We have that for digital PWM, the most of the spurious components are close to the bandwidth and difficult to be suppressed, whereas we have evenly spaced pulses, we push, in this case, it's no longer 8 times the fundamental, but it's just 4 times the fundamental frequency, the frequency at which we have pushed the energy of the spurious components. But we have also to observe that compared to the previous case, the amplitude of the spurious components is also less. It means that this is not more hard to be filtered. We can go ahead for 2 pulses. We can go to the very same considerations. 1 pulse, in this case, the digital PWM and the approach in which we have evenly spaced pulses are exactly the same. We get that the new patterns that we have introduced for 1/2 VDD, 1/4 VDD, 1/8 VDD, 1/16 VDD show better spectral properties than digital PWM. If we arrange these patterns so that to be non-overlapping, that is orthogonal, we can get that if we sum the waveforms related to these patterns, weighted by the weight of a binary number to be converted, at the end, we can obtain a digital bit stream that is a superposition of these signals which with favorable spectral properties that has a number of pulses which is exactly equal to the digital number to be converted. Okay, if we compare the spectral characteristics of the streams obtained in this way, that is actually the dyadic digital pulse modulation, compared to the digital pulse with modulation, we can say that now most of the energy is pushed at higher frequencies, while at lower frequency we have a very limited amount of energy that makes it very, very easy to be filtered. Also, if we look at the time domain waveforms, we can see that we filtered this DDPM stream compared, for instance, last plot with the output of a single bit sigma delta converter, we can observe that if we sample this filtered output at a given time instant, we have that the deviation of due to the ripple, to the residual ripple on this voltage from the expected value is always less than 1/2 least significant bit, which is not true for the sigma delta converter, in which we may have an error up to +4 -4 least significant bits. Okay, this makes this technique very suitable to the conversion of DC quantities. Actually, the good news is that this technique can be implemented by very, very simple digital hardware, which is actually a priority multiplexer driven by a binary counter. It works in this way. If we have the least significant bit of the counter to 1, that is every other cycle, we keep the most significant bit of the input to be converted. So we have 1/2 slots assigned to the most significant bit. If the least significant bit of the counter is 0 and the second least significant bit is 1, that means every other of the time slots in which have not been assigned to the most significant bit before, well, in this case, that actually are 1/4 of the total time slots, we apply to the output the second most significant bit, and so on. can be immediate to observe that the number of pulses which is assigned to each bit is equal to the weight of that bit in the binary representation of the input. Well, this technique has been adopted to design several digital to analog converters that have been integrated on silicon in 40 nanometers, and has also been adapted to perform analog to digital conversion. Thanks to this technique, we have developed the fully synthesizable 12-bit 110 kilosample per second digital to analog converter that shows ultra low area. Is just 270 square micrometers. It draws about 50 microwatt at 1 volt supply, but it works also fine down to 0.7 volts. And as not the state of the art of digital to analog converters, but shows quite reasonable figure of merits for what concerns the energy efficiency. Okay. We have also designed a 16-bit digital to analog converter that shows a very good static accuracy, that is plus minus 3.1 LSBs with digital calibration. And actually, the dynamic performance of this circuit are probably impaired by the clock signal, which was not very high quality, and was internally generated and was quite noisy. By the way, the 16-bit operation in static conditions has been demonstrated. Okay. Now, these results have been published in this paper. If you want, I invite you to see the paper to see the full comparison with the state of the art. A remarkable feature is that the linearity, total harmonic distortion, spurious-free dynamic range of this, if we neglect noise, just to see the linearity, is very, very good. Using this approach, we have also developed, we applied digital concepts like the concepts of graceful performance degradation by properly designing the binary counter and by properly designing the priority MOOCs. We made this circuit degrading gracefully when the supply voltage is overscaled or where the clock frequency is overscaled. This is due to the fact that the critical paths are shorter for the most significant bits, whereas they are longer the lowest is the significance of the bit in the digital input word. These are the results that basically confirm the graceful performance degradation as well as the reconfigurability of this digital to analog converter. As I have mentioned before, these are very simple, fully synthesizable digital circuits that have very released requirements in the filters. They work with a fully integrated, I omitted to say that they work with a fully integrated circuit that is a few thousand square micrometers, that is well integrated in the technology without an excessive area overhead are suitable to DC conversion, as we have said, and enable also concepts like digital, graceful performance degradation and power resolution scaling. As I have mentioned, by connecting these DDPM-based DACs in negative feedback configuration, and by including in the loop a successive approximation register, we developed two analog to digital converters that are based on successive approximation registers. Basically, the output of the DDPM DAC is updated based on this successive approximation register logic till the voltage at the input of this digital buffer reaches the trip point. By using the output of this buffer in the successive approximation register logic, we obtained at the end of the conversion the content of the input register of the DDPM converter is proportional, is linear with the input voltage applied in this circuit. By using the same approach but a different circuit configuration, we also implemented a DDPM-based analog to digital converter that is suitable to convert a current input rather than a voltage input. So it can be particularly useful for sensors which provide intrinsically a current output rather than a voltage output. Okay, we have measured the performance of these ADCs. They are 8-bit 2 kilosamples per second ADC. Again, the results of the measurements were affected by noise that made not possible to fully highlight the potential of the approach, but we can still observe very good linearity, 8-bit linearity, and also we can observe that the implemented circuits are very, very small, 3,000 square micrometers and 5,000 square micrometers. I have mentioned these analog to digital converters because the bitstream digital to analog converter, together with the analog to digital converter obtained using the bitstream digital to analog converter, make it possible to implement the generic input and the generic output in that system, very general digital-based analog system which I have introduced at the beginning. So, coming to the conclusions of my talk, I hope I have convinced you that there is an alternative approach to address the challenges of integrated analog interfaces in IoT applications, rather than adapting traditional design methodologies which are analog in concept to the requirements of digital process. One idea is to try to design digital circuits which implement the same functions of used in analog interfaces. I have shown how this is possible. This approach can be used to implement an operational transconductance amplifier and voltage reference. And I think it is quite obvious that being this circuit truly digital circuit, they fully take advantage of all the advantages of digital circuits. That is, they are scaling friendly. We have seen this for the digital OTA. They are matching insensitive. They are robust against PVT variations. allow ultra-low voltage, ultra-low power operation, are energy efficient, are reconfigurable, and finally allow also fast design with very low manpower, with very low effort, and very important portability across technology. What I want to say is that, of course, these are the very first prototypes that are based on these ideas. So they actually show the limitations. But what I want to say is that I do not see any fundamental performance limitation in this approach. So I suggest that working more on these circuits, on these techniques, and I also invite you all who are involved in working in research in this field to consider this alternative approach in the implementation of analog functions, because I believe it can be very, very interesting. I want to thank you for your attention, and that's all for my talk. I would like also to thank all the guys who work with me at the Politecnico di Torino. I know that one of them for sure is connected here, is following this talk, and for some part of this research, I would also acknowledge the funding of the European Commission. Thank you very much for your attention. I cannot hear you, Sergio.
Thank you, Professor Paolo Crovetti, for your very interesting talk covering this very large field from the OTA references, ADC, DACs, with mostly digital implementation, which is a very, very nice and very, very hot topic.
Thank you,
as you mentioned, on tackling the voltage reference, okay, the DC voltage reference, since you can use a very low, let's say, very low sampling rate for the ADC, and you tested that implemented with 12-bit ADCs. So what do you see for the voltage reference implementation? What's the power? The power constraint there comes from the high precision ADC. That's what taking most of the area and most of the power for the voltage reference.
Well, actually, in the first estimates of the power that I have made, I have found an activity factor, the percentage, the time percentage at which the ADC and the DAC are actually used is very low. It can be 10 power minus 4. So even if these blocks could be rather power consuming, I have assumed in that in the first paper, I have considered the state-of-the-art analog to digital and digital to analog converter. I have not considered the low power implementations at all. Considering state-of-the-art analog to digital and digital to analog converters, the average power consumption by using which can be obtained by using the virtual voltage reference in this duty cycled mode, active just for 10 power minus 4 part of the time, with a duty cycle that is 10 power minus 4, can be as low as in the nanowatt range. But I guess that if we consider possibly high resolution but simpler analog to digital converter and digital to analog converter architecture, the average power consumption can be much, much less. Let me also say, to better focus this point, what is the limit? Basically, what fixes the sampling time? assuming that the pseudo reference is sampled. So basically, the supply voltage is stored on a capacitor and is used as a pseudo reference for the ADC and for the DAC. The limit is given by the discharge time due to leakage of the capacitor. So it can be order of seconds.
Okay. Okay, we have another question here from Rodrigo Verdick, computer engineering student. He thanks you for your talk, Professor Crovetti. The question is, do you see any application of those fully digital amplifiers, circuits, as an ultra-low voltage SRAM sense amplifier? So question is, do you see application on this very dense digital SRAM as a sense amplifier?
As I think it could be considered the application as a sense amplifier. Actually, this was not the main application domain for which this technique has been focused, because we targeted, as also in the title of the talk, we mostly targeted the Internet of Things applications, but also biomedical applications. But I believe that this concept, probably including some positive feedback, could be also used, why not, as a sense amplifier. It should be definitely tested. Thank you for this suggestion.
Yeah, it's a comparator indeed, more than an amplifier.
Yes,
okay.
Of course, I have also tested that the circuit works nicely as a comparator. It has. I have also tested in my paper as a comparator. It works properly. What is worth being considered carefully is if this could be so appealing in the sense amplifier application.
Another question from Paolo Aguirre from the chapter here in South Brazil. Thank you for this very interesting and inspiring talk. May you comment a little bit about the maximum operating frequency of the proposed digitally based ADC or DACs?
Yes, maybe let me show. The operating frequency basically is dictated by the, let's focus, for instance, on the DAC. The operating frequency in this DDPM operating mode, since DDPM stream consists of 2 power n bits, the operating frequency is the clock frequency divided the 2 power n. By the way, it's worth being observed that these are not oversampled converters. Actually, these are Nyquist rate converters that generate an output every 2 power n clock cycles. Let me also say another thing, comparing to digital to analog converters featuring noise shaping. This approach could be more convenient, for instance, if you want to convert a DC value, because actually, even if you let me say one thing, that oversampled converters are intended, in my view, to approximate a signal, whereas these Nyquist rate converters are intended to approximate a voltage value per sample. Okay. I have answered properly to your question. So is the clock frequency divided the 2 power n. And for the successive approximation register-based ADC, that actually is based on this technique, it is 2 power clock frequency divided 2 power n divided the n bits, the n cycles requested for the successive approximation register algorithm.
Yeah, and it's indeed very compact implementation of the ADC.
Yes.
So area-wise, it's very compact. Well, no, we have this video available here in the YouTube channel of the chapter. I don't see any more questions. It's been a very productive and very interesting, and with the key concepts for analog signal processing with digital, mostly digital, implementation. Those are very interesting and frontier opening, let's say, work that came out of Professor Crovetti's group. So I thank you again, Professor Crovetti, for coming to this webinar and delivering such a very interesting and very let's say challenging for new concepts in terms of the analog and digital. So blurring the boundaries in a new and different way of our mixed signal. So that's very interesting, very important, and state-of-the-art results. Thanks a lot for coming, and
thank you.
I call every one of you here in Cyberland to stay tuned for the next October 14 distinguished talk on RF and microfluidics, antennas integrated microfluidics. So for your last statement and last words, Professor Crovetti, please, the floor is yours.
Thank you very much, Sergio. Thank you all for attending this webinar. I hope you found these ideas interesting. I am also glad if you have any comments, anything you want to share with me. I invite you to write me an email. I think there could be always good occasions for sharing new ideas, new concepts, new applications of these approaches. So thank you again, Sergio. Thank you all for attending, and thank you for giving me the opportunity to give this talk, and hopefully see you in other occasions. Thank you.
Thank you very much, and have a good day. Sorry for 2 questions that I missed here. There are still many questions outstanding from Pedro and Toledo, and who is co-author of the digital OTA, and also co-author Milton Klimek. So certainly we'll be seeing you in the chapter very soon. Thank you very much.
You're welcome. Bye.
So now we